didn't see you there. Welcome to my show. Today, on this lovely day, we are going to be talking about 4 subjects: states of matter, change of state, gas behavior, and graphing gas behavior. Shall we begin?
So, if you've ever seen a teapot, they're always on a burner boiling, and when you hear that whistle, it goes at a really high note. The reason that is because the gas particles are moving super duper fast because it's super duper hot, and they're trying to get out of the single hole getting out. So basically, gas is like a cartoon character. When the cartoon characters burn their butts, they go really fast, just like gas. So the teapots, when they're standing on the burner, the gas goes really, really fast until it leaves out the hole. For the different types of gas pressures, you have the one where if you divide the volume, the pressure increases. So when you divide this volume, the gas, it hits the outer walls at a faster rate than if it's in a bigger object. So it's basically like doing laps, and the smaller the track, the faster it goes, but if it's in a larger area, it's slower. So you have that, and then when you increase pressure, the people go faster. So it's like, if you have increased pressure, it's like your coach yelling at you to go faster. So, with this ball, we're increasing the pressure, making the gas hit the walls at a way faster rate.
Yeah.
This coach is like a drill sergeant. Just telling these gas particles, you need to run faster laps. Yeah. But the problem is, they have a therapist that's opening this really weird hole. So the gas is going off track. It's trying to go through here. So even with the pressure, they got a little hole that they can slip through unless you seal this hole, and then this whole baby's gonna inflate. You can see it's getting bigger. But here's the thing, if I make it like this, where I close off that hole and divide this baby's got a lot more pressure. I can tell you that much. But if we see, this hole is just letting out all the pressure. Just look through. This baby's getting inflated with gas particles going faster and faster.
They go back and forth, they zoom really quickly.
Particles in a liquid are packed almost as closely as particles in a solid, which explains the tension of the surface. The property is called surface tension. Surface tension is a result of inward pull, which brings the molecules on the surface closer together, making the molecules almost as compact as a solid. The surface of a water is so compact that when in action of being broken, it feels as if it was a solid. I'll be showing the strength of surface tension by throwing my 90-mile-per-hour fastball at the water. I will also be showing you how strong the surface tension is by throwing a lighter ball at it.
As pressure decreases, the balloon wants to fill up the space. If pressure increases, the molecules push on the balloon, making it smaller.
If you could see the particles in the air, you would see the gas particles moving in every direction. As gas particles move through the air, they spread apart, filling the space available. This is why gas has no definite shape or volume, just like when you fill up a balloon with helium.
Liquids, gases can flow, but unlike solids or liquids, gases will not stay where they are put. They have no set shape or volume, and they expand in every direction to fill up completely whatever container they are put into. Like when you breathe, your chest will expand and your lungs will fill up with air. So when you breathe in, air moves from your mouth to your windpipe to your lungs. But when you breathe out, this all happens in reverse.
So we're doing Boyle's law, and the two things that we're stating are pressure and volume. The highest pressure is 300 and the highest volume is 120. See, we put the 300 on the graph where it fits, and then same thing for the 250 under the 300 and the 200. And then we go like volume is across and pressure is up. So you put the 300 where it fits up on like the bar, and like the 300 and the 20 where they match, and then the 250 and 29 where they match. So vice versa for every on the graph.
So for the graph, what Orion was talking about is you're going to take your 300, which was the highest measurement for pressure, and you're going to put it up at the top line, meaning that's going to be like for example, we did 320 because that's how we got it to be even. So your 300, you're going to find out approximately where it's at on the graph. You're going to plot that point also with 24, it looks like, maybe 16 for that point, meaning that's where the pressure was and what the volume was at that point in time in the experiment. Your graph should end up somewhat like a curve, and with that's what the line's going to look like. For this, I don't think you would have to do a best fit line since it does end up like a curve due to the pressure decreasing or increasing, volume increasing or decreasing.
Solids are one of most three states of matter, and unlike liquids or gases, they have a definite shape that is easy to change. You see if you were to move a solid block, you wouldn't change its shape. If you were to spill a glass of water, then the water would change the shape. The particles that make up the solid are packed very closely together. That's all.
There are many different types of solids. Some solids that are made up of crystals are called crystalline solids. Salt, sugar, and snow are examples of crystalline solids. Crystalline solids can melt when heated at a specific temperature. In amorphous solids, the particles are not arranged in a regular pattern. Some examples of amorphous solids are plastic, rubber, and gas. Unlike crystalline solids, amorphous solids don't melt at a distinct temperature.
Boyle's law is a law stating that the pressure of a given mass of an ideal gas is inversely proportional to its volume at a constant temperature. Charlie's law is a law stating that the volume of an ideal gas's constant pressure is directly proportional to the absolute temperature. Directly proportional at one amount increases another amount.
Melting is the change in a state from a solid to a liquid. In most pure substances, melting occurs at a specific temperature called the melting point. KMT affects melting because in a solid, the strong attractions between the particles hold them tightly packed together. Even though they are vibrating, this is not enough to disrupt the structure. When a solid is heated, the particles gain energy and start to vibrate faster and faster. Initially, the structure is gradually weakened, which has the effect of expanding the solid. Further heating provides more energy until the particles start to break free of the structure. Although the particles are still loosely connected, they are able to move around. At this point, the solid is melting to form a liquid. The particles in the liquid are the same as in the solid, but they have more energy. To melt a solid, energy is required to overcome the attractions between the particles and allow them to pull them apart. The energy is provided when a solid is heated up. The temperature at which something melts is called its melting point or melting temperature. At room temperature, a material is a solid, liquid, or gas depending on its melting temperature. Think about what happens to an ice cube when you take it out of the freezer. The energy to melt the ice comes from the air in the room. At first, the added thermal energy makes the water molecules vibrate faster, raising their temperature. The change of state from a liquid to a solid is called freezing. It is just the reverse of melting. At its freezing temperature, the particles of a liquid are moving so slowly that they begin to form regular particles. When you put liquid water into a freezer, for example, the water loses energy to the cold air in the freezer. The water molecules move more and more slowly as they lose energy. Over time, the water becomes solid ice. When water begins to freeze, its temperature remains at 0 degrees Celsius until freezing is complete. The freezing point of water is 0 degrees Celsius and 32 degrees Fahrenheit. It is the same as its melting point. Evaporation. Vaporization that takes place only on the surface of a liquid is called evaporation. A shrinking puddle is an example of this. KMT affects evaporation because within a liquid, some particles have more energy than others. These more energetic particles may have sufficient energy to escape the surface of a liquid as gas or vapor. This process is called evaporation, and the result of evaporation is commonly observed when puddles or clothes dry. Evaporation takes place at a room temperature, which is often well below the boiling point of a liquid. Evaporation happens from the surface of the liquid. As the temperature increases, the rate of evaporation increases. Evaporation is also assisted by windy conditions, which help to remove the vapor particles from the liquid so that more escape. Evaporation is a complex idea for children for a number of reasons. The process involves the apparent disappearance of a liquid, which makes the process difficult for them to understand. It is not easy to see the water particles in the air. Boiling and boiling point. Another kind of vaporization is called boiling. Boiling occurs when a liquid changes to a gas below its surface as well as at the surface. You see the results of this process when the boiling liquid bubbles. The temperature at which a liquid boils is called its boiling point. As with melting points, chemists use boiling points to identify an unknown substance. KMT affects this because if a liquid is heated, the particles are given more energy and move faster and faster, expanding the liquid. The most energetic particle at the surface escapes from the surface of the liquid as a vapor as it gets warmer. Liquids evaporate faster as they heat up and more particles have enough energy to break away. The particles need energy to overcome the attractions between them. As the liquid gets warmer, more particles have sufficient energy to escape from the liquid. Eventually, even particles in the middle of the liquid form bubbles of gas in the liquid. At this point, the liquid is boiling and turning into gas. The particles in the gas are the same as they were in the liquid. They just have more energy. At normal atmospheric pressure, all materials have a specific temperature at which boiling occurs. This is called the boiling point or boiling temperature. Boiling point and air pressure. The boiling point of a substance depends on the pressure of the air above it. The lower pressure, the less energy needed for the particles of the liquid to escape the air. In places close to sea level, the boiling point of water is 100 degrees Celsius. In the mountains, however, air pressure is lower, and so it's water's boiling point. In Denver, Colorado, where the elevation is 1,600 meters above sea level, water boils at 95 degrees Celsius. Melting sugar. When melting sugar, you need to make sure that you have the proper materials for the experiment. Make sure that you have an adult supervision while you are doing this. You will need tin foil, a Bunsen burner, a ring holder, and sugar. When you start, make sure that the tin foil is folded into a boat shape. You need to make sure that you are wearing a heat glove so you do not burn yourself. First, you put a spoonful of sugar into the tin foil. After you get the sugar into the tin foil, you will start to apply the fire from the Bunsen burner to the sugar and wait until the sugar begins to crystallize. When the sugar cools down, it starts to turn into a black crystal known as carbon. KMT affects the sugar melting because they are moving so fast that they do not destroy the structure. The structure doesn't get destroyed, it gets weakened and separates and changes its shape. Boiling water. You will need a beaker and water. You will need a hot plate and an adult to supervise you. First, you need to plug in your hot plate and turn it on to start it heating up. Next, you need to put water into a beaker and set it onto the hot plate. You will sit there and wait for the water to boil, and that's how you boil water.
Keep her going. Keep her moving.
Faster, faster.
Keep her moving.
Let's go. Start it over.
David, you just be the drums. Thank you very much. Thank you very much for showing. I swear to God, Olivia.
Faster. Faster.
Connor, you gotta
Faster.
back up a little bit.
Faster. 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 Faster.
So today,